So let's do a quick review of the past lecture. We have been talking about constraint satisfaction problems, and then we started a new topic on knowledge, reasoning, and planning. I'm not going to spend too much time on that entire section, and I'm going to wrap it up today. And then I'm going to go on to uncertainty, knowledge, and reasoning. Okay, and we're going to spend more time on probability, reviewing probability, because that's going to be a critical component as we go forward. And it's an extremely important aspect of AI in general. Okay, so we need to have our concept straight in probability. So we'll be reviewing that as well. These are some of the review slides of the constrained, issues that we looked at in CSPs. And then we started knowledge, reasoning, and planning. And we spoke about what it is to have a knowledge-based system, deduction versus induction, types of logic. And then we spoke about different equivalences in propositions. We also then exposed you to the Prolog programming environment. And we did some little examples of Prolog. And this is useful. We won't spend too much time on this anymore, but it's always useful to know what a declarative language is like. Okay. So we said that in Prolog, you can declare facts. Okay. And those are prepositions. And then you can have predicates. Okay. And predicates are basically relationships, the objects, and the rules. Okay. So we saw some of those rules in the past. So let's just take a quick look at some of the rules that we looked at. So for example, we declared a parent function, we declared a father function, we declared a siblings function. So let's just try to review. How would you define, so we spoke about how to define a first cousins function, okay? So how would you define first cousins? Let's assume that you want to use a grandparent function, okay? So how would you go about defining a grandparent function? So help me out over here. So what would you start off with? Sorry? Yeah, so what would be the arguments to this function? First of all, let's decide that. So, okay, so you could have, well, you said male x1. Okay, now the arguments are going to be the people that we want to check whether they have grandparents. Okay, so well, we could and remember the grandparent could be either male or female. Okay, so basically what we want to do is in this function over here, we want to have two arguments. We want to have a grandparent and perhaps a child. Okay, and we basically want to show that this person here, G, is a grandparent of this particular child. So this is how rules are defined. Okay, and then we're going to have this particular colon and a dash, which basically means an if condition. Okay, so when is this going to be true? When is G going to be a grandparent of C? What are the rules that we've already seen? We've already seen siblings. We already have father defined. We've already have parent rule defined. Okay, we have male defined. So what do we need over here? When would G be a grandparent of C? If C is a father, if C has a father, so let's say that you're saying basically there has to be a parent, and the parent, let's say, who's going to be the parent? Okay, do we know who the parent is? So is it a variable or is it going to be a constant? It's going to be a variable. Now, variables are always defined as uppercase or lowercase. No, variables are uppercase. Okay, so here G and C are variables, and we know that because they are in the uppercase. Okay, remember in the past we've used lowercase. These are mistakes. This should be actually a lowercase over here. But here in the actual code, we are using lowercase. Okay. So the parent has to be somebody that we don't have it defined yet. So let's use the variable to define that. So we can say parent P is a parent of whom? Of C. Okay. So this has to be true. Then we're going to have a comma, which is going to represent an AND condition. So then what are we saying? So we found out the parent of C. And now what are we saying? P should be the child of G. So we don't have a child defined. We do have parent defined. So we can say that parent should be who? G should be comma and then P, right? So, and then we'll end with a period, full stop. That ends this particular clause. So basically this is saying that if if P is a parent of C and G is a parent of P, and both of these are true, this is an AND clause over here, then this entire clause is going to return a true statement. Otherwise, it's going to be false. Okay. So let's go on with first cousins. How would you define first cousins? So what should be the arguments over here? Should be one argument, two arguments? So there should be one or two arguments. Two arguments, right? So let's call them, they're going to be, let's say, siblings or children, right? So we can say C1 and C2. Okay. They're going to be in uppercase because they're variables. And what are the conditions for this to be true? So the grandparents have to be the same. Okay. So we're simply going to say grandparent of, so give me an argument over here. G. So we're going to say G and C1. Okay. So the grandparent of C1 and the grandparent of G comma C2 have to be the same. Okay. So if both of these, so basically what this is going to do is it's going to find all possible combinations of G through a search, which is going to have this true. Okay. And then it's going to see if that same grandparent also satisfies this condition. Okay. So it has to search through a lot, it has to do a lot of inferences. Okay. In this particular case, it may be a small tree, but you can imagine that this tree could be extremely extensive. So this here in this case, you have X1, X21, Y21, and so on. It's a relatively small tree, but you can imagine this could be extremely big. So it has to do a lot of inferences before it can actually find out whether this is true or not. G. Yeah, so good point. So what else do we need over here? Is that it? If you and yourself have the same grandparent, are you first cousins? No. So you may have to make sure that the person is not the same, right? So we have to make sure that C1 is not equal to C2. What else do we know? So if you and your brother have the same grandparent, are you two first cousins? No. So what do we want to also make sure?
Not the same parents.
So the parents are not the same. We already have defined that, right? Something called sibling. So how do we do that? So the siblings you should not be a sibling, right? So how can we encode that? We can say not sibling. What are we going to put as arguments? C1 comma C2, right? So C1 and C2 should not also be, and then we can put a full stop. I think that's pretty much all that we can think of, right? So you shouldn't be the same person, and you should also not be siblings. Okay?
Sir?
G.
Sir, can you please explain the purpose of we're using uppercase and lowercase?
Okay, so the uppercase, so lowercase in Prolog is always used for facts, okay, for constants, and uppercase is used for variables. That's just a syntax of Prolog, okay. So this should hopefully work. Let's see if this works. I do have this. So there are a couple of ways that you can check this out. One is that you could go on to this particular interface. So I've already loaded this. So if I consult with this particular knowledge base, It's going to open it and should normally, if it has additional clauses, I've already loaded it, so it's not showing additional clauses, but otherwise it normally shows, when you initially load this, this shows you have 21 clauses, which means, and how did we define clauses last time? So this is the knowledge base. So these are all the clauses, everything that ends with a period, okay? So you have male X1, male X21, and so on. Those are the clauses. Then you have the relationships. Then you have the functions. So this particular function is one clause, okay? So we've got all of these. If you add them all up, you should come up to 21 clauses. And then as I've tested over here, so let's do another test. What do you want to test over here? Do you give me a query? What would you like to query this knowledge base? We've already got parents defined. We've got grandparents. We've got siblings. So how would you find the grandparent of X32? So I would say grandparent who with a capital, okay, and then X32, okay, and then I end with a period. So that returns who is equal to X1. Okay, sort of sounds like Jeopardy. So this is your response. Now, how would I find all the possible grandchildren of X1? Can I use a grandparent query to do it? So how would I do that? Sorry? Define a new function. Do you think that's necessary from what we've studied so far?
Sir?
Grandparent X1 who.
Okay, yes.
Can use that, right?
So what you could do is you could have grandparent, and then instead of saying who over here, we say X1, who is X1 a grandparent of? Okay, so we could do this. Should this work? Should this work?
Yes, sir. Yes, sir, this should.
Some reason it's not working. Sorry?
Sir, there are two full stops, I guess.
Okay. So let's see, X1 grandparent, comma, who, dot. Execution aborted.
So you didn't give a question mark dash query sign, I think.
Sorry?
The query sign, you didn't give a query sign.
Let
last
me
time.
restart this. There might be a little problem with this. So let's double check. Prolog. And I'm going to load the, okay, grandparent of an X1 is supposed to be a grandparent. We want to know. Okay, now it's working. So it's found X31, Y31, X31, X32, Y32, Y33. Okay, so that makes sense. Any other query that you might want to think of? If you want to find out who is the sibling of, let's say, Y31, how would you do that? Sibling well, we want to know, is X31 a sibling of Y31? How would we do that? Whether Y31 is a sibling of X31. Sorry? Yeah, so that's fairly straightforward. Y31, comma, X31, and it returns true. Okay, so sometimes it can simply return whether the clause is true or not. But if there are more than one solutions for it, it will actually traverse. It will. So what is it actually doing? If you think about what Prolog is doing, is that it's got a bunch of facts, and then it's using the rules to get further facts. Okay, and that is not part of the existing knowledge base, but those are called inferences. Okay, so based on the existing knowledge, is trying to come up with a lot of inferences. Now, if you can imagine that, how many inferences, based on the rules that we have, how many inferences could you possibly have over here? So we've already defined a bunch of rules, right? We've defined father, we've defined sibling, we've defined grandparent, first cousins. Now, can you imagine that if you let this program run, all right, and you're going forward, which is called forward checking, then how many possible inferences can it draw? Would it be 1, 10, 100, 1,000, million? Number of relationships, right? How many relationships do you think that exist right now? I mean, is it a small number? Is it a relatively large number? Is it a few dozen? Or is it just 10, 5, 10? Less than a dozen. Well, if you think about it, if you think about all the individual inferences, so what we're saying is that X1 is a grandparent of Y31, right? X1 is a grandparent of X31. So each one of those relationships is actually an inference. So you can imagine all the combinations that exist of just grandparents and then first cousins. So how many first cousins are there? So there's 1, 2, 3, 4. So if you look at these, there's at this level 1, 2, 3, 4, 5, and each one of them could have a bunch of first cousins, right? So Y31 is a first cousin of Y32 and Y33 as well. Similarly, these guys are first cousins and so on. So you can just imagine how many inferences you can actually start drawing. So if you start doing what is called forward checking, then and you have a whole bunch of clauses, can you imagine how this tree will expand? This tree will have a lot of branches. Okay, so it can take forever if you actually try to draw all the possible inferences. Now, suppose that all you want to know, all you want to find out is who's the grandparent of X41. Okay, you're trying to find out who is the grandparent of X41. Now, if it uses the forward checking mechanism, does that seem like the best way? Or can you think of a better way to actually solve this problem? So what does forward checking sort of imply? Forward checking is saying that we'll start over here, we'll use all the possible inferences, and we'll start going in every possible direction. What does that sound like? Breadth first search, right? So in breadth first, you're making all the inferences, and you're just saying, okay, I need to have all the possible information about this knowledge base that I can possibly gather. And then after I've got all of that information, I'm going to see whether if any one of those relationships satisfies this condition that X41 has a grandfather or not. And I'm going to look at all of those leaves. There could be hundreds of leaves. And then I'm going to look for that one particular leaf. And I'm going to say, well, I found the solution. So that's one way of doing it. Okay, sort of going in this forward direction. And you end up with the leaves, okay, at the end. So this is your tree. Now, what could be another way? Depth first, right, naturally. So in depth first, you could go in one particular direction and you get to a leaf and then you sort of backtrack. But the question is, in which direction should you start off? So suppose you're looking for X41 over here and you're trying to find its grandparent. So if I do a random lookup in all possible directions of the depth first search, again, it could take a long time. Okay. So another possible technique could be what? I could simply start over here and say, I have X41 defined. Okay. It's a fact, let's say, and I'll just go backwards. So I'll look up all the relationships of X41 and see whether any one of them satisfy the condition of being a grandparent. Okay, so that's sort of like going backwards. So these are the two techniques. This is called forward chaining, and this is data driven. Okay, and it says starts with all facts and applies all inferences to extract more and more data. Okay, so you're building up. Imagine if you have a Wikipedia and you try to draw all the possible inferences, it would be probably more, it would take more time than you probably have left. Okay. So remember that we've already defined some of these. So if you look at the knowledge base, in the knowledge base, presumably we haven't defined it yet, but we have defined that X1 is a male, or X41 is already over here somewhere. So X41 has been defined to be a male. So we're going to that particular fact, and then we're working backwards. Okay. I'm not exactly telling you how you actually get to that particular, because we're not doing, this is not data structures where you actually figuring out how to actually get to X41. But presumably you have some mechanism to get to X41, and then you backtrack on its relationships. Okay. So there is some level of abstraction that I'm talking about. G. Yes, so all of these relationships are defined, but all the rules are defined, but you haven't inferred all of the possible connections. Okay, so if you're over here, you have defined this particular, you've defined the rules over here, the rules of the game. Okay, but what you haven't figured out is that, is X21 really a parent of Y31? Is X1 a parent of Y31? You haven't actually done that. But if you wanted to do that, you could, and you could possibly come up with all the possible inferences you can from the knowledge base. Okay, and you could come up with, so this is new data, right? So if you think about it, nowhere have we defined that X1 is a grandparent of Y31. We have defined a rule, and if you apply the rule, then you can come up with figuring out who is X1 all grandparent of, and then you'll find out that these are all the grandchildren. Okay, but before you actually run that, all those inferences, you don't really know that. Okay, so you've defined the rules, you've defined the facts, and now I'm asking you a question as to who is the grandparent of X41. So again, so if you're going with a forward chaining, then you find out all the possible relationships, and then amongst those relationships, which are right down at the bottom of the tree at the leaf level, you figure out, is any one of them satisfying this relationship? And that seems to be a bad mechanism, right? As you can see that it can, if you look at the pros and cons of this, the obvious disadvantage of this is that it's going to take a long time. Okay, and you may have, if you're just looking for one particular fact, why do you actually need to know who is, why do you need to know who is whose grandparent is X32 and so on? Okay, you don't need all of that fact. So why don't we just, it's sort of a need to know basis. Okay, if you need a certain information, you try to look at the goal. So essentially, like saying you look at the goal, and then you backtrack from the goal. Okay, so it's like sort of saying that you're at home and you're you're trying to get to IBA. Okay, main campus, your favorite destination. Okay, and one possible way is that you backtrack from IBA main campus and you go backwards and you try to find out what possible way actually leads you to your home. The other possible way of forward chaining is that you start from your home and you say, well, these are all the possible destinations that I could have, right? You could go to the beach, you could go to the cinema theater, and you could go to Lahore and so on. And you can imagine applying all those rules and finding out all the possible inferences. And then one of those inferences will say, by the way, oh, this is IBA, okay? And then, okay, then you say, okay, this seems useful. So this is what I was looking for. So it seems very wasteful, okay? So forward chaining can be very wasteful. Backward chaining basically says you're goal driven, okay, starts from the goal and works backwards, okay, and similar to DFS. So what are the pros and cons of forward chaining? Are there any pros? Can you think? I've told you all the cons of forward chaining, and it seems like the backward chaining is good, but can you think of when would forward chaining be good and backward chaining could be bad? Okay, so you're saying that if you're over here and right over here you have a relationship, and you don't actually, so, but again, in backward chaining, you're saying you start at the goal and you go backwards. So it's not going to be so bad. So backward chaining is not exactly like DFS. It's sort of like DFS, but it's basically saying you start at the goal and you work backwards. So it doesn't necessarily mean that you go all the way down to the leaf. Maybe that was a mistake for me to say that, but you could start with a goal and then you work backwards. Okay. So that's not exactly a good argument against forward chaining. Okay. Yeah, you build up on that thought. Right. So yeah, you're right. So you can see a parallel. That's a very good point. Very interesting way of looking at it. That here you're saying it's sort of like an informed search where you already have a goal. You may not have a heuristic, but you actually know what the goal. You have a good idea what the goal is, and then you're working backwards. Okay. And in the other case, you're completely uninformed. You're looking all over the place. Okay. So those are good thoughts. So basically, what we can say is that in case if you have a single starting point and you have many endpoints. So for example, you're trying to find out all the grandchildren of X1. Okay. Now you don't have a single goal. So there actually forward chaining might be more useful, right? When you say who, grandparent X1 who, then actually forward chaining might be useful. Okay, because you're looking for all the possible cases. You can't really start with each one of those grandchildren and work backwards. That may not be the best way. Okay, but if you have many starting points and one end goal, end point, okay, if you have one specific person that you're looking for example, a single grandparent, that's one goal, then it might be better to actually use the backward chaining. Okay. So these are two popular techniques that are used, and in fact, Prolog, I've been told, actually uses backward chaining. Okay, and there's more detail in the book, but I don't think that we need to go into a lot more detail on this particular topic. Okay, as there are a lot more interesting topics that we need to cover. So I'll stop over here as far as the knowledge base is concerned, and now we will start off with the next major section, which is going to be uncertainty. G. Yeah. Right. So let's take a look at that. Right. So so you could apply it, but over here, remember, we are not really talking about a knowledge base here. This is not a knowledge base problem. This is a different category of problems, which is the constraint satisfaction problems. In CSP, you could combine, it doesn't necessarily mean that a CSP problem can't be combined with knowledge base and can't be combined with machine learning, can't be combined with, but right now we're studying each one of these independently. So if you say that, what if you have a knowledge base in this map coloring problem, how would you solve it? And then you could apply a combination of those techniques. Okay, but when we studied this, we weren't using a knowledge base at all. Okay. At some point, it would be very interesting if you start, maybe we'll do that, is to start combining these different chapters and to see how we can actually, and maybe this is something that you could do in a later project. We don't have a project in this course, but you can think of AI projects in the future where you actually combine some of these thoughts. Okay, and that's in fact how most of the challenging problems in the AI actually are resolved. Okay, when you study deep learning, for example, some of the best algorithms in deep learning don't just use deep learning. Okay, they're a combination of a lot of other different algorithms. Okay, so now let's talk about uncertainty. Now, if you think about uncertainty, most of things in life, in real life, are actually stochastic, are probabilistic. Okay. Can you think of one thing which is perhaps not probabilistic? Are there things which are not probabilistic in your life? Your grades, for example, in the quiz. So is your quiz grade right now, absolutely final. No, as far as you're concerned, but I've actually finalized it. Okay. So do you think it's actually final? Perhaps.
सर आपके
Yeah.
मूड पे डिपेंड करता होगा.
So I've actually checked it, but there could be a possible error. For example, there's a possibility that your entire LMS could crash tonight. Okay. And we don't have that saved. And we redo the whole thing. And then we come up with make a mistake, or we actually figure out that you maybe cheated. Okay. Or something else. So essentially, if you think of any possible scenario in real life, it's actually, there is a certain level of uncertainty. Okay. Is the sun going to rise tomorrow? Is that certain? It's not really certain, Qiyamah aa sakti hai. You could have doomsday tonight, or you could have, as they say, a spaceship could come in from nowhere and could blow up the sun. So there is a level of uncertainty everywhere. Of course, some of those things are ludicrous, like the latter example about the sun exploding. And the level of probability of that happening is so negligible that it's frivolous to actually talk about that. Okay. And the quiz example is also frivolous, by the way. So hopefully the LMS is good, right? And just scores are stable. G.
So we can say that time is like, we cannot stop time. So that can also come in this.
You're saying time is, I didn't quite get you, but you're saying that time is perhaps is definite.
Yes.
Yeah. So that's something very good. Actually, I think there's a hadith in which the Prophet said that, you can solve almost every problem, any infliction, except old age. And old age is basically time. Maybe they have a solution for that, but I don't know. So, one day we're all perhaps going to die. And that's one of the certainties that I think we can say for sure. But other than that, most other things in life are actually uncertain. Okay. And you can think of almost everything that you're doing today is uncertain. So if you're trying to come to IBA and you say, well, I've got an hour left and normally it takes me 15 minutes. Am I going to get there within an hour? Is that 100% sure? No, obviously not, because your car could break down. You could have a meteorite fall on you and so on. Anything could happen. Okay. So most things are uncertain. Now, when you're doing search under uncertainty, have we actually looked at that before so far? Think back. In the semester, have you looked at uncertainty in any case, search under uncertainty?
A chance as a player tha.
Say that again.
Chance as a player humne dekha.
Chance as a player, exactly. Good recollection. So we saw this particular example, right? We said that Y is, for example, is the player Y that you're playing against. And we said, what if Y picks the wrong move 10% of the time? So we were doing a probabilistic analysis over there. So we've already come across such an example. And basically what we were saying is that X over here is trying to maximize its expected utility. Okay. So you're not saying we know for sure what its utility is in different actions, but we're trying to say what is the expected utility if it takes this particular action? What's the expected utility if it takes this other action? Okay. And this is what we've already studied. So now, as we go forward, probability is going to become more and more important. So what I'm going to do for the next half an hour, 35 minutes is try to take you over a review of probability. Okay, now you've already studied statistics, intro to statistics. Hopefully this is going to be a review. Okay, but let's take a quick look and see how much of it you actually remember. Okay, so probability review. What's a sample space? So let's say that you're rolling a dice. A die as a single dice is called. What's the probability space? What's the sample space? Sample space is what?
1 to 6, the possible
1
outcomes
through 6,
of a
right?
die.
So this would be a set from 1 to 6, right? N would be what in this case? N would be equal to 6. If you're tossing 2 coins, what's the sample space?
Head and tail.
Head and tail, is that the only one? All the possible combinations, heads, tails, tail, head. Okay, so you can see that the sample space is all possible outcomes. Now these are called outcomes. Okay, any individual result of an experiment is called an outcome. Okay, Are these outcomes mutually exclusive? So are each one of them mutually exclusive? Can you have head and tail at the same time as head in the same as a result of the same experiment? No, each one of them is mutually exclusive. When you roll a die, you could have one of those possible numbers, but you can't have 1 and 2. Okay, so it should be clear that the outcomes are mutually exclusive. Okay, now for each one of those outcomes, we have a probability defined, right? So clearly, you have for each one of these, the probability is 1 upon 6. For each one of these, the probability is 1 upon 4, right? And another condition is that for each one of those outcomes, so if you look at this, and this is equation 13.1 from your book, and it's simply, and they use a slightly different notation. So they're saying that the probability for each one of those outcomes, if you sum them up over all possible outcomes, has to be naturally equal to 1, right? Because probability of each one of these has to be adding up to 1. All right, same case over here. That's kind of obvious. Now, what are events? And these events are referred to as propositions here when you're talking about AI. So somebody define an event. How is that different from an outcome? You have to speak up. You got a mask and big auditorium. No, that's a percept. Okay, so if you think about it in terms of an agent and an environment, that's not what we're talking about. Just forget about AI right now as well. Okay, just think about simple intro to statistics. This is a revision right now. We're not really talking about how it links to AI right now. That will be done later on. But think about an event. Just think about in terms of the dice and the coins. Can you think of an event on these two experiments? Are these outcomes or are these events? These are outcomes. So what's an event? Sorry? If you re-roll the die, okay. Okay, so let's say you toss it, if you toss it twice, okay, or you roll the coin twice, then what you're saying is that could be defined as an event. So outcome is the result of an event. Well, that's one way to define it. Any other clarity on this? Okay. A lot of different definitions. Anybody who's absolutely sure what an event is? G. Yeah. That's an experiment. Okay, so when you toss a coin, that's called an experiment. So I think people are not very clear. Actually, event is a combination of outcomes. Okay, so for example, in this particular case, if you say that the outcomes, I define an event A to be the set of outcomes 1, 2, 3, and 4. Okay, so this could be an event which is a bunch of outcomes. Okay, so a set of outcomes is essentially an event. Okay, it's an important definition. Okay, similarly, you can define another event which is 4 and 5. Okay, so 4 and 5 is an event which is saying that your outcome is either 4 or 5. Okay, and in that case, the event will be true. Okay, so event is linked to the outcomes, but not as you decided that you don't go from event to outcome, you go from outcome to events. Okay, it's in that direction. Now, what is the probability of the event? Okay, and so in AI, we call events propositions. We don't call outcomes propositions, we call events propositions. Okay, and basically what we say is that if you look at all the possible combinations of, if you sum this up, it should come up to the probability of that particular event. But let's hold on to that thought. First of all, let's try to figure out what is the probability of an event. So what's the probability of A? What is it?
1/6. Oh,
Is it? I think
4/6.
4/6, right? Why is that? Because basically this is a sum of all the individual probabilities. So this is the sum of probability of 1 plus all the way up to probability of 4, which is coming out to be 1/6 and 4. So it comes out to be 4/6, right? What's the probability of B? It's clearly up 2/6. Okay. Now, what's the probability that A and B, so the joint probability that both event A happens as well as event B happens? So it's basically the probability of 4 happening, which is essentially 1/6. Right? Everybody's clear on that. What's the probability of event AG? Yes. So A, B are all now events. Okay. So A is defined as an event over here, and this is a set of outcomes. So 1, 2, 3, 4, 5, 6 are the outcomes, but an event A is defined as a set of outcomes. Okay. So B, you could also have an event which is defined as simply 1. Okay. So I could define C as an event 6, for example. That event is equivalent to a single outcome. All right. But generally it's a bunch of events. It's a set of events, a set of outcomes. So how would you calculate the probability of event A happening or event B happening?
5/6.
So this would be 5/6. And how did we calculate that? This is probability of A plus the probability of B minus the probability of A and B, right? So we remember this. So far so good. Okay. Now, what are mutually exclusive events? So can you define mutually exclusive events on this particular state space?
Such which do not have intersection.
Which are disjoint, which don't intersect. So can you give me an example of an event A and B which are mutually exclusive?
1, 2, 3.
So you could say 1 and 2, and this could be 3, right? So those would be mutually exclusive. How would we calculate? So here is an example: 1, 2, 3, and 4, 5, right? So they're mutually exclusive. And in this particular case, the probability obviously that A and B both happen has to be equal to 0, okay? Simply because they're mutually exclusive. Now, what is conditional probability? Okay, so here we've, let's say that we have the events are defined A as 1, 2, 3, 4, okay? And event B is 4 and 5. Now, how would we define a conditional probability that given that B event has already happened, how would you find out the probability that A will happen? Okay. How do you find this out? We already have some information. So we already know what probability A and B is. We already know what probability A or B is. We also know what probability A is, and we also know what probability B is. Okay. So how do you find out what is the probability of A given B? So don't think of the equation. Think about this diagram over here. It makes it easier. So given that B has happened, what is the probability of A? Just tell me the answer, looking at this particular
1 over
case.
6. 1 over 6?
1 over 2.
Somebody saying 1/6?
1 over
1/2. Who said 1/2? Okay, good. So why is it 1/2? So basically what you're saying is that we know that event B has happened, so it's either 4 or 5. Okay. Now we're saying that given that the outcome of that experiment was 4 or 5, it's not the others. What is the probability that event A happened? Which means that out of 4 and 5, which one are we looking at? We're looking at
4.
Outcome 4. Okay. What is the probability that outcome 4 will happen given that 4 and 5 have already happened? What's the probability of that? Given that they're all equally probable, 1 upon 6 is 1 upon 2, right? So that should be clear. So basically, it's 1 upon 2. Now, how did we come up with that? Then you write an equation now for it, backward chaining, all right? Go backwards. You've got the solution. And this, a lot of times, this is a good way to solve problems, right? You don't know a formula, right? But you know intuitively, you look at a particular problem and you say, can I solve this problem? And this technique will come in very handy. In fact, this is how, most of my life I've solved problems. If I'm looking at, a new problem, then I try to see, can I come up with an example, a trivial case of that, and see what's the answer of that. And I try to find a solution. Then I see, well, can I generalize this? Okay. And then you come up with a generalization. Then you try to see whether I can encode it and so on. So what did we actually do over here? Why did we get half as the answer? Sorry? Say that again. Okay, very good. So you can see now it's coming back to your mind, right? Recollection. So basically what we're saying is, what is the probability that A and B happened divided by the probability of B? Okay, does that make sense? And why are we saying that? Because the probability of B over here is what? Is 2 upon 6. Okay, the probability of A is 4 upon 6. And so the probability of A and B is this particular case, okay, which is 1 upon 6. And the probability of B is 2 upon 6. So this becomes half. All right. And you can see that logically from this diagram as well, that is going to be half. Okay. What's the probability of B given A? So now we're saying that A is given. So it's going to be 1 upon 4. You can simply see that because why is that? You're looking at 4 is the only possibility. And you're saying, what is the probability that 4 happens given that 1, 2, 3, and 4 happened? Okay. A has already happened. So we know that one of those numbers has already come up, 1, 2, 3, and 4. And now what's the probability of B happening? The only case that B can happen is that the number comes out to be 4, which is 1 upon 4. Okay. So this is conditional probability. Okay. The chain rule. Now, the chain rule basically says that if you have non-independent events, okay, then A given B is, we already seen A intersection B divided by probability of B. Hence, we can say that probability of A and B can be written as probability of A given B times probability of B. Okay, so all I'm doing is I'm taking this and putting it over here, and I'm multiplying this on the other side. Okay, so probability of A given B comes up, and probability of B comes out over here. Okay, so I'm just cross multiplying. So far so good. Okay, now we know that A and B is the same as probability of B. This is commutative, right? Probability of B and A is the same as probability of A and B, right? That's commutative. So you can see that this is also true. You can write it this way. So once you've written it, and let's use a slightly shorter notation, you could say that in general, for example, if you have probability A, B, and C, you could say that this is probability of A given B multiplied by probability of B, or probability of A given the others multiplied by the others. And this can also be written as a combination of this. So probability of B comma C could be written as probability of B given C multiplied by probability of C. So you can see that there is a chain rule. All right. Okay, so if you have probability of A given B, C, and D, how could you write this? Sorry, if you have a probability of A, B, C, D, this is the joint probability. Now, how would you write it as a chain rule? You could start by saying probability of A given B, C, and D, right? Multiplied by probability of, well, let's make it simple initially, B, C, and D. Okay. So this is the first part. Then what you could do is you could break this up and you could say this is basically the probability of B given C comma D multiplied by probability of C comma D, right? Similarly, you could break this up and you could say this is C comma D multiplied by probability of D, okay? So this is what the chain rule is. It's fairly straightforward. And this comes up directly from this equation that you sort of intuitively guessed, okay? Now, what are independent events? Okay, so we've talked about conditional probability, we've talked about mutually exclusive events. What are independent events? Okay, independent events are when the probability of A, let's say A and B are independent, the probability of A does not have any impact on probability of B and vice versa. Okay, so given that one event has already happened, the other event has no, it's indifferent. Okay, so give me examples of two events which are independent in the real life. Is your final exam grade, is your final course, is your final marks on this course independent of your first quiz results? Final grade in this course independent of your first quiz? It is not independent, right? It's definitely, that's part of the equation, right? Is your second quiz independent of your first quiz? Most likely, hopefully, if I'm being fair and if there are no questions in common, then it should be independent. Although there is some commonality, right? So somebody who does extremely well in the first quiz, do you think they're going to do well in the second quiz? But even then, think about human nature, right? A person who is a straight A student, so there is a high probability that if they've done well in the first quiz, then I can predict that they will actually do well in the second quiz. In fact, a lot of times I do grading this way. When I'm grading the final exams, I look at the best students first, and I know that they will probably have high results. So I start by looking at their results, and I know that, okay, these are the easy ones. And the ones that are most difficult to grade are the ones which are doing the worst, okay, because they're making all kinds of mistakes. So in fact, those two quiz results are in fact not really independent. So you can think deeper and you can see that actually there is some joint probabilities in there. Okay, they're not completely independent. There was a question online. G.
I was asking, like, in that sense, wouldn't that make your marking biased? Because you're basing the marks of the students based on what you think they're going to get instead of what they're actually going to get.
Yeah, that's a good question. You can now put me on trial, right? Yeah. So I claim that I'm not guilty to that because I'm quite independent. Although I'm looking at their results, but you could say, well, there is a level of I could be guilty of that. And if you put me in court, actually, in a lot of cases, the name of the students are purposely not written in the exam paper simply to avoid this kind of bias. Okay, so if I am guilty of that, there is a possibility that somewhere in my 20-year career at IBA, I have actually committed that crime. Okay, I've thought that this is a good student, and I've blindly checked their marks, and I've actually been guilty of bias. So this bias does creep in. It creeps in almost everything that you do. Okay, think about your own life, and you'll come across that you'll have biases. How do you pick a friend? When you first came to IBA, how did you pick a friend? Were you completely unbiased, or did you look at a person and you said, well, how are they speaking? How is their mannerism? So there is some kind of a bias in almost everything that we do. Okay. And you've caught me on a good point. I might have been biased, so I'll try to avoid that and not do that in the future. So going forward, when would two events be independent? So can you write an equation for this? Okay.
So probability of A plus probability of B.
So it would be probability of A plus the probability of B. So should be sum or should be multiplication? Because remember, if you have probability of A plus probability of B, you could run into trouble because sum could actually be greater than 1 as well. Okay. It might be possible, but I'll double check that. But it's not a sum, it's actually a multiplication. Okay, so you can replace that by a multiplication. In this case, if these two events are independent, okay, then what is the conditional probability? Probability of A given B. So what this would this be?
Probability of A.
So this would simply be the probability of A, simply because why? Because probability of A is not impacted by probability of B. Okay. So, and you can use the actual equation to do this, because what this is saying is that the conditional probability is the joint probability divided by probability of B, but the joint probability is simply probability of A times probability of B from this equation over here. And so probability of B cancels out, and so you're simply left with probability of A. Okay. Similarly, you could say that the joint probability, you also have a problem if you have this at the bottom. So let me try to remove that. So similarly, if you have, if A, B, and C are independent, then it's simply the joint probability is simply the product of those three probabilities. Okay. So far, so good. Now, tell me if these events are independent or not. A, I'm defining A as, again, 1, 2, 3, and 4. You've done a single die experiment. You've thrown a die. And B is 4 and 5. Okay. So are these two independent? So how would you check it out? The condition is that the probability, the joint probability has to be equal to the product of those two. Okay. So the event A and B happening should be equal to the product of those two. Now, what's on the left-hand side? This is the left-hand side, this is the right-hand side. So what's the probability of A and B both happening? 1 upon 4 times 1 upon 2. Well, you could just look at this. The probability that that A and B both happening is the probability that the outcome is 4, okay, which is simply 1 upon 6, right? What's the product of these two? What's the probability of A? 4 upon 6. What's the probability of B? 2 upon 6, right? So what does that come out to be? 8 upon 36, which comes out to be 2 upon 9, right? Is the right-hand side equal to the left-hand side?
No, sir.
No. So what's the logic? Why are these two not independent?
So because they have a common of 4.
So because 4 is common over here, okay? Because you can see that the fact that A has happened has an impact on B, and similarly the fact that B has happened has an impact on A. Just intuitively looking at that, we've already got that experience, right? That these two are related, okay? So they're not independent. What about this case? So here A is 1, 2. Sorry.
Independent and are they mutually exclusive?
Are these two the same thing? Good question. Does mutually exclusive imply that they're independent or dependent? Okay, just hold on to that thought, because I will ask you this question in a couple of minutes. First, let's take a look at this and get this thought clarified before we try to combine these thoughts. Okay, so the next issue is, are these two events independent or dependent? So A is 1, 2, and 3, and B is 3 and 4. So what's your intuitive answer? Looking at this, 4 was common, so naturally they're dependent, right? Okay, let's do the calculation. What's the joint probability on the left side? Left-hand side is 1 upon 6, right? Because the probability of both of them happening are 3. Is the outcome has to be 3, because that's the only intersection. Left-hand side, right-hand side is equal to what? So 3 upon 6 multiplied by 2 upon 6, that comes out to be 6 upon 36, which is 1 upon 6. Independent or dependent? So they seem to be, if they're independent, then the left-hand side is equal to the right-hand side in this equation, right? So they are independent. So why are these independent? Can somebody have an intuition for this? Why are these two independent? And if I had a little prize, I would give that prize out to the person who can answer that intuitively. Why are these two independent? The fact that B has happened has no impact on the probability of event A happening. Sorry? Condition का flaw भी हो सकता है, all right? So you're challenging one of the fundamental equations, all right? You'd better go, and that's a very big statement. Okay, we're not at that level yet, okay? So there's an intersection over here as well, but they found that they were not independent. Think. Now let's look at the problem. Let's look at this actual problem. It says that I found out that B has already happened. Okay. What we're basically saying that the probability that A will happen, given that B has already happened, if we're saying that they're independent, what does this imply? This should be equal to
P of A.
Probability of A, right? So it doesn't really matter whether B has happened or not. So just looking at this, we're saying that B has happened, and we know that 3 or 4 has already happened. Now, what we're saying that the probability that A will now happen is independent of that. Can you just look at this and tell me why?
सर वो P of A भी 1 of 2 है, और अगर हम वो देखें तो 3 और 4 में से एक है खाली 3 upon, तो 1 over 2 दोनों equal हैं इस वजह से.
Yeah, I think you're getting to the right. So you have a little chocolate from my side, of virtual chocolate. Okay, so because you're virtually here, so basically you have the right thought. Okay, so if you look at the intuition basically is right here. The probability of A happening, given that B happened, it seems to be independent, because you can see that if B has happened on both sides, A happening and A not happening are equally weighted. Okay, so the probability of A happening is 1, 2, and 3. The probability of A not happening is 4, 5, and 6. Now, B is straddling both sides equally. Okay, so the fact that B has happened doesn't weigh either probability of A happening or probability of A bar, as I like to write it, probability of A not happening. Okay, because B is straddling both of these equally. Okay, so you can now have an intuition that just because B has happened, you are not actually changing the weight of either A happening or A bar happening. Okay, so this is an interesting example. And similarly, you can think that probability of B given A should be equal to probability of B, and you can go through that same reasoning. Okay. Now let's take a look at the earlier question. What if you have mutually independent or mutually exclusive events? Okay, so A is now mutually exclusive to B, right? So A is 1, 2, and 3, and B is 4 and 5. Now, what's the relationship between mutually exclusive and independent events? Okay, are these independent or dependent events? You're saying that they're independent. Okay, so let's do this check. What's the probability of A and B happening? 0. What's the right hand side saying? What's the probability of A happening? 3 upon 6 multiplied by 2 upon 6. Are these two equal? No. Okay. So they're not independent. Okay, why is that? You can't have B, right? So actually, they're completely dependent. The fact that B has happened means that either 4 or 5 have already happened, which means that A is impossible to have, right? Because all of these are mutually exclusive. So when you have mutually exclusive events, then there is a very high probability that they're going to be not independent, okay, depending on the particular scenario. In this particular case, they're not independent. Here's another example. Now, let's think of other examples where they are independent, okay? Or let's think of this example. Let's say you throw 2 dice, okay? Do 2 experiments. You throw 1 dice, and then you throw a completely, it's not the same, well, it's the same dice, but it's not, it's not weighted, or it doesn't have a bias, okay? And you throw it again. Are these 2 events? And you define A as the probability, as A is the event that either 1, 2, or 3 of the first die happens, and you don't care about the second die, and you define B as the event that 4 and 5 happens in the second die, and you don't really care about the first die. Now, are A and B independent or dependent? Now they seem to be independent, right? Because these are 2 separate experiments. What can you think of a real life example where they could be actually dependent? In real life, you could have imperfections, right? So maybe the die is actually slightly weighted, as sometimes happens in casinos, right? So there's a high probability that 1, 2, and 3 will happen. It never falls on 4 and 5. So in that case, you can see that there's a link. But if these 2 events are independent, by definition, okay, then they will be, so actually by definition, we're defining that they're independent, okay? So I'm not going to draw a diagram over here, but by definition, we're saying that they're independent events, okay? This is sort of one of those trick questions. This is kind of obvious that even if you do try to do the calculation, you're doing the same calculation on both sides, okay? So that was 4 examples. Now there's another, we have a few more minutes, and I finally figured out that watch is actually a little fast. So you have about 4 minutes. So let's look at this law of total probability. Okay, I don't know if you've come across this particular law, but it's quite a basic law. Okay, what this says is that, let's say that here's your sample space, and B sub I are chosen to be mutually exclusive events. Okay, so for example, you could choose an event B, which is simply 1 and 2. Okay, and B bar or not B would be what? So this was a dice. So this B bar would be what? 3, 4, 5, and 6. Okay, now are these mutually exclusive events? Yes, clearly, because you can see that's obvious. In that case, you can define any other event A. So this is another event A as a bunch of conditional probabilities based on B. Have you come across this before? No. Okay. So let's define this. So this would be defined as follows. Probability A could be said to be probability A given B, okay, multiplied by the probability of B plus the probability of A given B bar multiplied by, fill this out, probability of
B naught.
B bar, okay, B not B or whatever, okay. So this is how you would define it. In other words, if you have B sub I in general, you would say probability of A can be splitted up into probability conditional, bunch of conditional probabilities, A given B1 multiplied by B1, A given B2 multiplied by B2, and so on. In other words, in the simple case that B and B bar exist, which are mutually exclusive, you could say that probability of A is the probability of A given that B happened multiplied by the probability of B plus the probability of A given that B bar happened multiplied by B bar. Okay, so this is something called mutually exclusive. Okay, and this is going to come in handy when we talk about a very important theorem, which is called Bayes theorem. Okay, how many of you have already come across Bayes theorem? Hopefully, in Intro to Statistics, you've come across this, right? So it's a fairly straightforward theorem, and it's almost intuitive. Okay, and once you look at it, you say, why it's such a big deal? Okay, but in fact, it's an extremely big deal. Why is that? Because of the implications that the Bayes theorem actually has. Okay, and so Bayes theorem is simply a cross multiplication of some of these terms. All right, you've already seen this, A given B. You've already seen this several times already today. All I'm going to do is now I'm going to bring this onto this side. Okay, probability of A given B, A and B, and we're going to write this, we're going to multiply this on this side. So this is probably, so we've already seen this. This is simply what's called the chain rule. Okay, so now we're going to write this top part over here. Okay, we're going to take the chain rule. So we're going to take probability of the intersection of this is going to be replaced with this chain rule. Okay, so we're going to say probability of the joint probability is this portion, and the bottom portion is going to come up here. Okay, simple mathematics. Okay, we're just multiplying the bottom. But now the implications of this are very interesting, and I'm going to leave you with a question. This is an example of the application of Bayes theorem. Suppose that you observe an IBA student, okay, and this particular student knows a lot about technology. All right, and we're going to say this is a proposition that he knows a lot about technology. This is a fact. Okay, and the question is he or she more likely to be a CS student or a non-CS student? So this person knows a lot about technology. What's your initial guess? CS student, right? Better be a CS student, because CS students know a lot about technology, right? Sorry?
Why?
Non-CS भी हो सकता है. But now the question is, what is your likelihood? What do you think? What do you think is more likely? I'm not saying that that's zero. The probability of being a non-CS student is zero. I'm saying which is more likely. So how many of you think it's more likely to be a CS student? Okay, most of you. But some of you are undecided. Why are you undecided? Tell me why you're undecided. Or you didn't think about it. But if there's a reason why you're undecided, tell me. Ji. Okay, so you're saying that so now the issue is we need to understand the next part, and we need to say what is the probability that a CS student would be interested in technology. Given that is a CS student, what is the probability that he will know about technology, and what is the probability that a non-CS student will know about technology? So now let's take a guess. Okay, what do you think this probability is? 75%. What about a non-CS student? BBS student ko kitna, how much will they know about technology? Unko bolna aata hai, right? So they're great speakers, but if you ask them the Bayes theorem, they won't know what it is, right? So let's say this is 10%, right? No, nothing. But I'm going to take slightly more realistic values. Okay, so I'm going to say the probability that a computer science student knows about technology is 90%. Okay, and I'm going to say that a non-CS, as you're saying, some of them do know about technology, is lower, but it's still 30%. Okay, but what does this say? How does the Bayes theorem calculate it? Okay, and I'm going to stop over here. I want you to calculate this on your own and think about it, and come back next time and tell me what does the Bayes theorem tell us.